Hi everybody, in this video we are going to talk about Lewis structures and how to draw them. So if you recall, Lewis structures are diagrams that describe the bonding of a molecule in question. The lines represent the bonds, and these could either be single bonds, double bonds, or triple bonds. And non-bonding electrons are written as dots surrounding the atoms. Two non-bonding electrons are called lone pairs. So in this example, this is a Lewis structure for oxygen gas, O2. And as you can see, in yellow, the two non-bonding electrons can be considered a lone pair. And this is a double bond written as two lines. And yeah, oxygen gas looks like that. Now let's actually learn how to draw these. So I've compiled a few steps for you to follow, and go in order in these steps, and if you are stuck, then you can move on to the next step. If you manage to finish the structure without moving on to the next step, then you could stop there. But usually you tend to go at least to step 3, and step 4 and 5 are there just in case you still can't figure it out. So let's figure out how to draw Lewis structures using this nice procedure. Number 1, count the number of valence electrons and include the loss or gain of electrons into the total count for polyatomic ions. So you might be wondering, how do I find the number of valence electrons? Well, there are two ways. The first way is to find the number of s and p electrons in the outermost shell of the electron configuration. So this goes back to chapter 4 regarding electrons and their electron configuration. So for example, if you want to find the valence electrons for argon, argon's electron configuration will be a bunch of stuff, and then at the end it will have 3s2 and 3p6, and 2 plus 6 is 8 valence electrons. So that's one way to do valence electrons, by looking at the valence electron configuration, specifically for the s and p sublevels, because for our purposes, we are looking at the main group metals, which is groups 1, 2, 13, 14, 15, 16, 17, and 18, and the valence electrons for these 8 groups are located in the s and p sublevels, and we are not going to be dealing with transition metals, actinides, or lanthanides in this video, so don't worry about the valence electrons for those, since they are a bit more complicated and won't be discussed in this video, since this is just an intro to Lewis structures, and we are going to just focus on the 8 groups that I mentioned before. So this is the first way to determine the number of valence electrons for main group elements. Now the second way is honestly the easier way. This is by looking at the group, and the group will tell you how many valence electrons there are. So for group 1, which is the first column, these elements have 1 valence electron. For the second group, 2 valence electrons. For the 13th group, which is the one that starts with boron, they have 3 valence electrons. So just think of the 13 becoming a 3 by removing the 1 in front of it. And the 14th group, which has carbon, has 4 valence electrons. The group starting with nitrogen, or the 15th group, has 5 valence electrons. The 16th group, starting with oxygen, has 6 valence electrons. The halogens, or the 17th group, which is the one that starts with fluorine, has 7 valence electrons. And the noble gases, the 18th group, has 8 valence electrons. So that's a nice way to know the number of valence electrons for a given atom. Now, moving on, let's take a look at the procedures. So we talked about how we have to count the number of valence electrons and include the loss or gain of electrons for polyatomic ions, since they have a plus and minus charge, which indicates extra electrons or missing electrons. So the extra or missing electrons in polyatomic ions are applied to the needed atom, as we'll see in an example. Number 2, draw a skeleton between atoms and put single bonds between them. The central atom is usually the one written in the formula first, and the central atom is just the atom that's written in the middle of the Lewis structure, and that central atom is typically the one that needs the most electrons. Then subtract these electrons, meaning the electrons that are in the bonds, and 2 electrons are in one bond, and you have to subtract these electrons from the total valence electron count. So we'll do this in a question soon so it becomes more clear what this exactly means. Step 3, determine how many electrons each atom needs to become an octet, or in other words, having 8 valence electrons. And of course, there are exceptions which we'll talk about in step 4. So give each atom its proper number of valence electrons first, and you have to keep the bond in mind when you're doing this, and I'll show you all this when we do an example. Each single bond between 2 atoms adds an extra electron to each atom due to sharing. So if it's a double bond, then it'll add 2 electrons to the atom, and that will increase its number of valence electrons by 2 and get it closer and closer to 8. So this next step is situational and only occurs if there are odd number electrons. And if this occurs, then always fill the octet of the more electronegative atoms, since they hog electrons more, so they would naturally have their octet filled over other atoms. And this atom might also be the central atom, and leave the odd number electrons to the less electronegative atoms, meaning that for the less electronegative atoms, they will not have an octet in this case, if for some reason you have an odd number of electrons. And one of the most important parts to step 3 is that when an atom doesn't have enough valence electrons, make sure to change your single bonds to double or triple bonds if needed. And this is a very important step since some atoms might need a double or triple bond in order to work. So make sure to do this step and see where your structure goes. And if steps 1 through 3 fail, then you have to go to step 4, which is addressing another situation. Step 4, break the octet rule if you have to, and do an expanded octet, which means that there are more than 8 valence electrons per atom if the atom is in period 3 or higher. So if the central atom is in period 3 or higher, then it can break the octet and do an expanded octet. And there's something called a deficient octet. Now, this occurs when an atom has less than 8 valence electrons, and this occurs for hydrogen, since hydrogen only needs 2 electrons, and it occurs for beryllium, which can form up to 2 bonds, and boron, which can form up to 3 bonds. So keep these in mind when you're doing Lewis structures. Now, step 5 is the last and final step, and you only do this step if you're desperate. So you can actually move electrons, or in this case valence electrons, since all the electrons we're talking about in this video are valence electrons. So you can move valence electrons from one atom to another to increase the number of bonds one atom makes, or decrease the number of bonds one atom can make. So this is confusing, but let's take an example. So oxygen has 6 valence electrons. It needs 2 more valence electrons to be 8. So what if we decide to take 1 electron away from oxygen? If we took 1 away, then oxygen would have 5 valence electrons, and it would need 3 more valence electrons. So because it needs more valence electrons, once you remove an electron, then it has to make an extra bond. So this is how step 5 works, and do not attempt this step unless you feel that it is necessary. Now, after you finish writing the Lewis structure out, you have to check for something called the formal charge. The formal charge is the charge assigned to atoms, assuming all atoms share electrons equally. And this is not the actual charge of the atom. It's just a concept that people like to use to check for the stability of a Lewis structure. So I'll show you how this works, but let's find out how to calculate formal charge first. The formal charge is equal to the number of valence electrons typically found in an atom minus the non-bonding electrons in the Lewis structure for the atom minus the number of bonds attached to it. So if it's a single bond, it's worth 1. If it's a double bond, it's 2. And if it's a triple bond, which is technically just 3 single bonds combined together, although this is not accurate, but you could think of it that way, that's equal to 3. So after drawing Lewis structures, check the formal charge on the atoms and make sure the structure you are drawing makes them as close to 0 as possible, because low formal charges correlates to stability. And this is because things with a positive or negative formal charge typically are more reactive and are more high energy, which correlates to lower stability. So for example, if you see a formal charge of +2 or -2, or even more than those numbers on a structure, then this is typically a red flag that your structure isn't stable or reasonable. And the only case where this is not true is if there are no other possible structures for the structure, and in that case, then I guess having a +2 or -2 or even more formal charge is fine. But that's only when you actually can't do anything about it. But if you can do anything about it, and you have a really high formal charge, then I suggest that you change up the structure and do some creative things to it to lower the formal charge, and make sure that you're following the rules on, steps 1 through 5, unless it is not possible to follow those rules. And that's really rare. So just follow the rules from steps 1 through 5 and the step about formal charge, and you should be good. So I know I've been scrolling through these examples that we are going to do, but let's do an example for the formal charge on this oxygen atom. This one. So the formal charge on the oxygen atom will be the number of valence electrons that the atom usually has, which is 6, minus 4 non-bonding electrons, minus 2 bonds, since it's a double bond, and this is equal to 0. So the formal charge on this oxygen is 0, and since it's the same situation for this oxygen, then the formal charges on this and this are 0. So because they are 0, this structure is reasonable and stable. So now that we've talked a lot, I think the best way to learn Lewis structures is just to draw them, honestly. So for this example, I drew the Lewis structure for iodine solid, since iodine in nature is found as a solid, and iodine needs 1 more electron, so a single bond for both iodines will be sufficient, and this is because iodine has 7 valence electrons and it needs 1 more to be stable. And how do I know it had 7? Well, remember the periodic table? Iodine is in group 17, the halogens, and halogens have 7 valence electrons. So the first step is to count the number of electrons. So since each iodine has 7 valence electrons, the total number of valence electrons is 14. Step 2, draw a single bond between each atom. Now I did that, and you have to subtract by 2 because 1 bond has 2 electrons, so you have 12 electrons left to use. Now, step 3, you have to put the remaining electrons as, lone pairs or non-bonding electrons around the atoms. So I put 6 on each, since remember, the iodine naturally has 7 valence electrons, and it already donated 1 to the single bond, so it has 6 valence electrons left, and these valence electrons are non-bonding, so I put them around for both of them. And notice how this is the Lewis structure for iodine solid, or I2, because both iodines have 8 valence electrons after sharing, and they're both happy. So this is the correct Lewis structure, and we have 0 valence electrons left to spare, and we're good. Let's try out this. How do you draw the Lewis structure for water? Well, step 1, count the number of valence electrons. Each H has 1, so there's 2 there, and oxygen has 6, so there are 8 valence electrons total. Step 2, put the atom that needs the most electrons as the central atom, because that was one of the steps, which was the central atom is usually the one that needs the most electrons, but in this case, it's not the one written first, but it usually is, but in this case, it is not. So, O will be in the middle, and the 2 H's will be attached to it by single bonds, and since there are 2 bonds, then you subtract 8 by 4 to get 4 electrons left, since each bond holds 2 electrons. Alright, let's do step 3. Add the remaining valence electrons as non-bonding pairs. So I need to make sure that each atom has the right number of valence electrons. Now hydrogen has 1, and that's true because it donated 1 to the bond, and I don't have to add any extra electrons to any of the hydrogens. But the oxygen naturally has 6 valence electrons, and it donated 2, 1 to each single bond, so there are 4 electrons I have to add onto this, and it'll be 1, 2, 3, 4. And notice that when I added the 4 non-bonding electrons, now I have 0 electrons, and thus this is the Lewis structure for water. So not that hard, right? And if you notice, the oxygen now has 8 valence electrons since it has 2 bonds, which adds 2 valence electrons. So oxygen had 6, then 2 bonds make it have 8 valence electrons in total, since technically this oxygen is sharing this, and since there are 2 electrons in each of them, then the oxygen technically has 8 valence electrons, and it's happy. Now each hydrogen only has 2 valence electrons, since 1 bond is worth 2 valence electrons, but it's happy regardless because in step 4, remember, hydrogen only needs 2 electrons since it's 1s2. Now you might be wondering, why didn't I check the formal charge? Well, I did, and let me tell you, the formal charge on each of the iodines is 0, and the formal charge on each of the atoms in H2O is also 0. So because they're all 0, these structures are stable and reasonable. So I didn't show you the math because I'm sure you could do it by yourself, since I already showed you an example. And don't worry, I'll do some examples with formal charge for harder questions, but now is not the time for that. Third question. Now this one is weird. How do you draw this one? Where will the atoms go? We don't have just, one in the middle. There are technically many middles to this. And typically the first element is the central atom. So let's take a look at how many valence electrons there are. Each carbon has 4 valence electrons, so 12 there. Each hydrogen has 1, so 8. Each oxygen has 6, so, 1 times 6 is 6. So the total number of valence electrons is 26. So that's a lot of valence electrons to take care of. How do we do this? Well, let's draw the structure. So the central atoms, I'm assuming, are the carbons, so I'll draw them near the middle, and I'll put a bond between them, and I will add the hydrogens. So you have to keep a note that carbon needs 4 more valence electrons. Now this carbon already has 1 valence electron because each bond adds 1 valence electron. So this carbon needs 3 more bonds to add 3 more valence electrons to make it 8. So let's add the rest of the hydrogens, because one hydrogen needs just 1 bond to add 1 valence electron to the hydrogen, and we'll have 2 and it'll be happy. So let's just say there's an H there, an H there, an H there. And this carbon is happy since it has 4 bonds, since 4 bonds add 4 valence electrons, and carbon has 4, so 4 plus 4 is 8, and it's happy. So this carbon already has 2 bonds, so it needs to have 2 more bonds to make it 8 valence electrons in total. So let's just add another 2 H's. Now we have 3 more H's to go, so I'll add the first 2 H's, and watch what I'm going to do. O has 6 valence electrons, and it needs 2 more valence electrons to be happy. So I need to put 2 bonds on oxygen. So I could do this and do that. Now, oxygen has 2 bonds, which is adding 2 valence electrons to oxygen, and the hydrogen, our remaining hydrogen, is there, and it has 1 bond, so it's happy. So if you notice for this question, the number of bonds it makes is equal to the number of valence electrons it needs, and that's a really good tip that you should think about when drawing these structures. Now, how many electrons do we use for these bonds? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bonds. So if there are 11 bonds, then we have to subtract 26 by 22, since 11 bonds times 2 electrons in each bond is 22. We're left with 4 electrons left, and we move on to step 3. We have to add the remaining electrons as non-bonding electrons, and we typically add these to the ones that need more electrons. So this oxygen needs more electrons since it's supposed to have 6 originally, since, it donated 2 to the bonding pairs, but it has 4 left after donating 2 to each of the, single bonds. So it has 6 valence electrons usually, but it donated 2, 1 to each single bond, and we're left with 4 electrons that needs left. And hey, what do you know? Those 4 electrons that we have left over can be added as non-bonding pairs, which this oxygen needs very badly. So we just drew the Lewis structure for C3HAO, and it looks like that. So let's move on to the next question. NH4+. Now this is a polyatomic ion, so we have to be a bit more careful. Step 1, how many valence electrons? Well, this has 5. This is, 4, since each H is 1. And notice how the plus means that 1 electron was removed. So that means that this here has to be subtracted by 1, since, normally it would have 9 valence electrons, but since it's a plus, it means that one of the atoms lost 1 electron, so we have to factor that in. So we have 8 valence electrons in total. Now let's do step 2, draw it out. So N is in the middle, because N needs the most electrons, and the only places where the hydrogens can go is around the N, so let's just draw 4 hydrogens attached to the nitrogen in the middle. And notice how you're like, wait a second, nitrogen only needs 3 bonds since it needs 3 valence electrons, but as you'll see, it'll all work out in the end. So 4 bonds equals 8 valence electrons, so 8 electrons originally minus 8 is 0. Hey, we don't have to add any more valence electrons. Now, there's a problem. Do we have the full octet for each of these atoms? Well, for the hydrogens, they need only 2 since they're an exception. So these 4 hydrogens are happy since they have 2, since each bond that they have is worth 2 valence electrons. And the nitrogen, the nitrogen has 4 bonds and therefore has 8 valence electrons that it's getting, 4 from itself and 4 from its hydrogen buddies. So since each bond is worth 2, then the nitrogen has 8 valence electrons technically after sharing, and thus the nitrogen is happy. So notice how there is a +1 charge. Now this is saying that one of the atoms lost an electron. So which one of these 5 atoms lost an electron? Well, it's probably nitrogen, because nitrogen usually has 5 valence electrons, and since, according to this diagram, it only donated 4 electrons, 1 to each of the 4 bonds, then that means that the nitrogen had 4 valence electrons to begin with, just like carbon, and thus that means that nitrogen must have lost a valence electron in the process. So in this case, nitrogen is the one with the +1 charge. So let's now calculate the formal charge, and if you're wondering, for the previous problem, all the formal charges were 0, and you can do that using math, but I'm just going to tell you that all the formal charges were 0. Now for this one, not all the formal charges are going to be 0. If I choose one of the hydrogens, I know that hydrogen has 1 valence electron naturally, it has 0 non-bonding electrons, and it has 1 single bond which is worth 1, and this is equal to 0, so the hydrogens have a formal charge of 0. Now what about the nitrogen? Well, the nitrogen typically has 5 valence electrons, and it has 0 non-bonding electrons. Now I don't know why there's a dot there, but it's not supposed to be there, so I just erased it. So there are 0 non-bonding electrons, and there are 4 bonds, or 4 single bonds, so it's worth 4 in total, and the formal charge on nitrogen is +1. So this is the formal charge, and notice how the +1 is not a good sign since we need the formal charges to be all zeros. But in this case, there's no other way to draw ammonium, so therefore the +1 is actually okay, and we'll leave it like that. So let's move forward to the next question. Carbonate, CO3 2-. Now, how do we tackle this? Well, let's count the number of valence electrons. Carbon is 4, oxygen is 6, 6 times 3 is 18, and since it's 2-, that means that 2 atoms, or maybe 1 atom, gained a total of 2 electrons. So there's an excess of 2 electrons, so 2 extra electrons, and you add them together, and you get 24 valence electrons total. So how do we draw the skeletal structure? Well, C is there, and let's draw a single bond to each of the O's, since, carbon needs 4 valence electrons, while the oxygens need only 2 valence electrons. So we have 6 bonds, so there's 18 electrons left to use. Now step 2, well, I guess I just did step 2 by doing that. So step 3 is to either put the electrons where they need to be or add more bonds. So in this case, I'm going to add more bonds since carbon seems like it needs an extra bond. So how do we do this? Well, if carbon needs 1 more bond, since, it needs 4 valence electrons, let's just do it to one of the oxygens, because why not? And now, let's add the valence electrons. So, let's add the valence electrons, and here we go. So, this oxygen over here has already a double bond, and that means that this oxygen already contributed 2 electrons to that bond. So, that means I've had 6 valence electrons, and it contributed 2 to the double bond. That means it must have 4 valence electrons left over. So those are the non-bonding pairs. For this oxygen, well, 1 bond, so donated 1. So 6 minus 1 is 5. So it has 5 left, and this has 5 left too. Now you're like, uh-oh, how many electrons do we have left after that? Well, if you think about it, we added 1 extra bond there, so that's worth 2 electrons, and we added a total of 5, 10, 14 non-bonding electrons. So 14 non-bonding electrons added, plus the 1 line, which is worth 2. That's going to be 16 electrons used. So we have 2 electrons left after that exchange. So where do these 2 electrons go? Well, it goes to where it needs to go. Now that's kind of vague, but it makes sense. Here's how. So look at this oxygen. This oxygen seems like it's not happy, since the oxygen typically needs 8 valence electrons, but the bond only donated 1. And notice how there are 5 valence electrons here, and there's 2 in this bond, so the oxygen technically has 7 valence electrons right now. So it's not very happy. So how do we make it happy? Well, since this is a polyatomic ion, it has this 2 minus, which means 2 extra valence electrons, which is also shown there, incidentally. Then we could add these 2 extra electrons to the oxygens. And remember from the step over here that said that we can add the electrons to the more electronegative atoms. So what we're doing here makes sense, since we're adding the electrons that are left over to the more electronegative atom, and in this case the more electronegative atom is oxygen and not carbon. And in the first place, oxygen needs it, so let's do it. So if it has 7, then we need to make it so that it needs 1 more. So we could do this by drawing a bond, or we could just simply add it. So if we add it here and we add 1 here, notice how we just add 2 non-bonding electrons, so there's 0 left. And this could be considered the Lewis structure for carbonate. So you could either do it like this, put this in brackets, and write a 2- in the corner, since it is a polyatomic ion with a charge of 2-, or you could draw it like this. And this is just drawing it with the formal charges, such as the minus, or, in the ammonia with the plus. So because we drew the Lewis structure for carbonate, let's now talk about a topic known as resonance structures. These are alternative Lewis structures that mean the same thing. Now, in the next video, I'll talk more about what this means, but for now, just think of resonance structures as alternative Lewis structures that mean the same thing. So, in these three examples, you can see how this structure for carbonate is the same thing as this structure for carbonate, the only difference being that this double bond is moved down here instead of staying up there. And for this one, notice how this double bond shifted to here. And in this case, for the resonance structure for carbonate, all you can do is move the double bond around and you will get all the resonance structures. So keep a note that these minuses are the formal charges, and I'm just drawing it on the diagram. Or you could write carbonate as, brackets C with, the O's, with the 6 electrons on each of these O's, and then the double bond O with 4 electrons. And you would put this all in brackets and put 2 minus, but you would not put the formal charges on the atoms. So you could either draw it either this way with the formal charges and without the bracket, or this way without the formal charges but with the bracket and the charge of the overall structure. So now let's look at another polyatomic ion. Let's look at nitrate. So nitrate has how many valence electrons for step 1? Well, let's see, 5, and each oxygen has 6, so 18. And there's an excess of 1 electron in the structure since it's -1 charge overall. So it's plus 1 electron. And this would be 24 valence electrons overall. So let's get to drawing. So let's draw the skeletal structure and find the number of electrons left over. So we drew 3 bonds, 6 electrons, so 24 minus 6 is 18 electrons left. So now for step 2, we can do one of two things. Well, actually, step 2 was just drawing that. Now I'm talking about step 3. For step 3, we can either add non-bonding electrons or add more bonds. So which one should we do? Well, let's think about this for a second. Nitrogen needs 3 bonds to be happy. So, therefore, this is okay since nitrogen needs 3 valence electrons or 3 bonds. So let's add non-bonding electrons to the oxygen since they seem to need it more. So, oxygen originally has 6 valence electrons, and I donated 1 to make the single bond that it's sharing with the nitrogen. So it has 5 left over. So let's do 5 for each of these and see where we're at after that. So we do 5 for each, that's minus 15 electrons, and we have 3 electrons left. So where should these 3 electrons be? Well, I noticed that each oxygen needs 1 more valence electron to have 8 valence electrons in total. So why don't we add 1 valence electron to each oxygen to make them happy? So if we add 1, 2, 3, we use up all 3 electrons, and now we have 0 electrons. So are we done? Well, not exactly. This nitrogen has only 3 bonds, and it's not very happy because it wants 8 valence electrons and not 6. So how do we fix this? Well, we can't do step 4, the extended octet, since none of these elements are in period 3 or higher. Now, what about step 5, where we start moving electrons from one atom to another? I think that could be really helpful. So I didn't mention this in the 5 steps, but by moving electrons from one atom to another, you can also technically change an electron pair or a lone pair into a bond by doing this movement. So let me show you how that works. So this lone pair can actually move itself here in order to make a bond, because remember, a bond is just 2 electrons. So if we erase these 2 electrons, which is our lone pair, and we move it and change it into a bond, it'll look like that. And notice now, by adding a bond to nitrogen, nitrogen is now happy because it has 8 valence electrons, and this oxygen is happy since it has 8, and this oxygen is happy since it has 8, and the last oxygen is also happy. So this is the official Lewis structure for nitrate. Well, it's not the actual thing you should write. What you should write is this. So you could do it in 2 ways. So let's first draw the structure we made. So N with 2 single bonds attached to an O, and each O has 6 non-bonding electrons, and there's a double bond there with an oxygen. And you could do it in 2 ways. You could put it in brackets and put a minus there, since remember nitrate is minus, or you could do it like this. So I'm going to draw it super duper quickly, just like that. And you could calculate the formal charges for each of the atoms. So the formal charge on this would be -1, and you don't have to put the 1 there, you could just put minus. For this one it would be minus, for the N it would be plus, and for the O up there it would be 0 or neutral, so we could just ignore that. So you could draw it like this, with the bracket and with the charge at the top, or you could write it like this. So 2 ways to draw the nitrate ion. Quite amazing, right? But if you really want to draw it officially, you have to do its resonance structures. Just like for carbonate, the official Lewis structure were considered to be all 3 of these, since all 3 of these were contributors to the structure of carbonate. So let's draw all the structures for nitrate that contribute to the structure of nitrate. Or in other words, let's draw the resonance structures for nitrate. So the 3 resonance structures for nitrate are this. So I'm going to write nitrate in the bracket form with the minus sign on the top right corner. I'm going to write N with a double bond starting at the top, and the O going here, and the O going here. And then I'll draw a double arrow to show that the first structure of nitrate can resonate to the second structure of nitrate, which might look like this. So we have to move the double bond around, and this time the double bond will be on the bottom right. And I drew too many electrons for that. And let me draw the last oxygen. And then the last resonance structure would look like this. And the double bond would be on the bottom left this time. And let me just draw this really quickly. And there you go. Let me put the minus signs as well. And these are the resonance structures for nitrate. So now let's take a look at phosphate, and let's see how we draw this. So let's count the number of valence electrons. There are 5 here, and each oxygen is 6, so 6 times 4 is 24. And there's an excess of 3 electrons, which is why phosphate is -3. So it'll be +3, and the total number of valence electrons would be 32. So how do we go about drawing this? Well, what I like to try first is put the first element in the middle and put the oxygens around it. And notice how phosphorus only wants 3 valence electrons because it has 5 valence electrons. But if you remember Rule 4 stated that elements that are in period 3 or higher can do an extended octet. So I'm taking advantage of that property to do this. So since it can have an extended octet, I am going to put as many electrons as I need around phosphorus to make this work. So 4 bonds so far, so that's -8, and that would be 24 electrons left over. Now, I could start putting electrons around each of the oxygens, so let me do that. So I think that each oxygen should have 6 electrons to be happy. So let me just do that. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. All the oxygens have 8 valence electrons if you consider a bond as 2 valence electrons after sharing. And look, the phosphorus is happy too. because it has 8 valence electrons. So is this the Lewis structure for phosphate? Well, yes, but let me tell you something. This would not be the best Lewis structure for phosphate, because if you check out the formal charges, the formal charge on phosphorus is +1, and all these are going to be -1. And notice how there are a lot of formal charges going on, and when you're drawing Lewis structures, you want to have as many formal charges equal to 0 as possible. So is this the best that we can do? Well, I think we could do better. Let's try doing a few things. Let's try moving electrons around. So here's a neat little trick that I learned from experience. If you have a minus formal charge and a plus formal charge, in order to make those zero out, you could simply move the electron pair and move it into the bond, and when you do that, you get this. So you get that, you get you get this, and you get this. Oh, wrong placement. There you go. So look at this new structure. All I did was I moved the lone pair and I turned it into a bond. And notice what happens is that the formal charge on these 3 oxygens is now -1. The phosphate has a formal charge of 0, and the oxygen on top has a formal charge of 0 now. So by moving an electron down, I essentially canceled these two out, and you end up with an even better Lewis structure. So I would say that this is the better Lewis structure out of the two, and it would be more stable, despite phosphorus having too many valence electrons. But it's okay, since phosphorus is in period 3, and things in period 3 or higher can have an extended octet. So I'd say this is a real winner here. And remember, the more formal charges that are equal to 0, the better. And in this case, there are 2 atoms that have a formal charge of 0, as opposed to no atoms having a formal charge of 0. So I'd say this is superior, and I'm going to draw out resonance structures for phosphate. So let me clear the ink, and let's draw the resonance structures. This time, I'll do it using the formal charge method. So I'm going to put the P in the middle, and then the O is there with 4 electrons, and then I'm going to do that, and that, and that. Now let me put the minus charges on the things that need the minus charges, since these 3 oxygens have a formal charge of -1. And let me draw the resonance structure. So you're going to draw a double arrow, and let's move this double bond to here. So let's do that. So this would be like this, and this would be a double bond, and then this would be a single bond, and this would be a single bond. So I'm going to draw all 4 now. So here are the resonance structures for phosphate, and notice how for the oxygens that have single bonds, I'm putting a minus charge there because the formal charge on those oxygens is minus. And I think I misplaced the minus here. I think it's supposed to be up here actually. Sorry for the confusion. But here are the 4 resonance structures for phosphate, with the minuses on the ones with the single bonds. So I think I did it correct, and there you go. That's how you do the resonance structures for phosphate. Now let's look at the next question. BeF2, beryllium difluoride. Now if you remember, beryllium is a metal, and why do metals form covalent bonds? Aren't covalent bonds only formed between nonmetals? Well, in this case, this is an exception, and beryllium is one of the metals that can form covalent bonds. And in the future, you'll see that metals can actually form bonds, but we won't look at that here since that has to do with another topic that's not related to the simple Lewis structures that we are doing right now. So, beryllium difluoride. Remember beryllium in Rule 4, it stated that beryllium can form only 2 bonds, and that's all it needs to form. So it could just do this. And let's count the number of electrons. So beryllium has 2 valence electrons, each fluorine has 7 valence electrons, so there are 14 total, and that makes 16. and after drawing 2 bonds, that makes 12. And 12, well, if you think about it, we can distribute these evenly among the fluorines, because each fluorine needs 6 more valence electrons to have 8, since this is already 2 and it's being shared. So let's draw it. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That is beryllium difluoride for you. And notice how all the atoms are happy except for beryllium, because fluorine has 8 valence electrons, but beryllium has only 4, but that's fine because it's an exception. So moving on, this is called nitrogen monoxide or nitric oxide. Nitric oxide is just a special name for this. So let's figure out how to draw the Lewis structure for this. First of all, how many electrons does this have? Well, 5 plus 6 is 11. And this is actually the first time that we have an odd number of electrons. So when we have an odd number of electrons, one atom is going to have an octet while the other is not. So let's figure out how to do this. So let's connect the dots first. N and O are connected. So that's 11 minus 2, and that's 9. So 9 valence electrons left to use. Which octet do we fill first? Well, I think the octet we should fill is oxygen, since oxygen is more electronegative and wants to hog the electrons. So let's fill the octet for oxygen first. 1, 2, 3, 4, 5, 6. Now oxygen has 8 valence electrons and is happy. Now what about nitrogen? Well, for nitrogen, it gets leftover electrons, so 9 minus 6 is 3, and this gets 3. So you might notice that nitrogen only has 5 valence electrons, and we want to get nitrogen to have as many valence electrons as possible. So we have to get it as close as possible to 8, and that would be as ideal as we can get. So what can we do? Well, the oxygen can share its electrons, so this electron pair can be thrown down here. And if that happens, then it will look like this. And notice how the oxygen still has its octet, but the nitrogen is closer to its octet. Now it has 7 valence electrons. So notice that when oxygen shares its electrons, both of the atoms are still happy in the end. Well, in fact, nitrogen becomes happier since it gets more valence electrons. So sharing is caring in this case, and we can't share any more electrons, or else nitrogen will have too many valence electrons. So this would be the ideal Lewis structure for nitric oxide or nitrogen monoxide. Now there is another way to draw this. So let me show you how to draw this in the other way. So what I would do is that I would instead fill the octet for nitrogen. So I would draw N and O, but I would fill the octet for nitrogen first before filling the octet for oxygen. So there's 11, and now you subtract, I think, 8, and you get 3. So it'll look like that, and the nitrogen can share one lone pair to make another bond, and in the end you get something that looks like this. So this time the nitrogen has all the electrons it needs, while the oxygen is missing one valence electron that it needs. But this is superior to that, since this is filling the orbitals for the more electronegative atom. So if I were to draw a Lewis structure, this would be the superior Lewis structure in the case. So now let's do our last Lewis structure, N2O, also known as dinitrogen monoxide or nitrous oxide. Now N2O is also known as laughing gas. So let's draw the Lewis structure for laughing gas. So there are 2 nitrogens, so 10, and oxygen is 6, so 16. So now let's draw the skeletal structure. I'll assume that the 2 ends are together because, the 2 ends are together there. And our central atom is the atom that needs the most electrons, which is nitrogen. So I think this will work out. So 16 minus 4 is 12. We have 12 left to put. So how about this? Let's fill the octet for oxygen first, since oxygen is the more electronegative atom. So I'm going to put a bond there, and I'm going to put 4 non-bonding electrons. So that's -6, and we have 6 valence electrons left to play around with. So how do we do this? Well, what if we made a bond here to satisfy the octet for nitrogen, since it has 8 now, and that would be 4. And let's just add the remaining 4 around here, and look at that. All of these atoms have their octets filled. This has 8, this has 8, and this has 8. So coincidentally, this is a perfect Lewis structure to use. And it's your choice whether you want to label the formal charges. So for the previous question, we could have labeled the formal charges on this atom. Well, actually there were no formal charges. Just kidding. Let's look at this. What are the formal charges? This nitrogen has a formal charge of 5 minus 0 minus 4, which is +1. And we don't have to add the 1 since that's implied with the plus. And the other nitrogen will have a minus formal charge. So look at that. It's your choice whether you want to put the formal charges or not, but in this case I am, because it makes the image clearer. So this is a Lewis structure for laughing gas, and although there are other resonance structures for laughing gas, I will do that in the next video when I show you how to draw resonance structures for things like laughing gas. And I also want to add one very important note, and this will help you check your work along the way. So the note is that when you add up all the formal charges, the sum of the formal charges should add up to the charge of the substance in question. So for example, for N2O, the -1 and the +1 added together equals the charge of the N2O, which is 0 or neutral. Now another example of this is for phosphate, PO43-. For phosphate, notice how the formal charges add up to -3, and that's the charge of the ion. So that's all for this video. I hope you learned a lot. And remember, if you have a method for doing Lewis structures that is easier for you and still yields results that are reasonable, then go right ahead and do that. So that's all I want to say. Thanks for watching and have a nice day.